Every physics textbook you've ever opened, every one, is built on an assumption so deep that nobody even states it anymore. Your teachers never mentioned it. Your professors skipped right past it. The assumption is this: things happen in order. First this, then that. The ball hits the window, then the window breaks, the match strikes, then the fire starts, cause comes first, effect follows. It's not just a rule of physics. It feels like a rule of reality. Like the skeleton holding the whole enterprise together. Remove it, and what have you got? Chaos, nonsense, a world where nothing means anything. And here's what I need to tell you right at the top before we go any further. At the quantum level, that skeleton isn't there. It's not broken. It's not bent. It is absent. In the quantum world, events can happen in no definite order at all. Effect does not wait politely for cause. A photon can go through room A before room B and through room B before room A at the same time, not one or the other, not we don't know which, both simultaneously. And the experiments, real experiments done in real laboratories with real equipment and published in real journals, confirm this. You're going to want to resist what I'm about to show you. That's fine. I resisted it too. Resistance is the appropriate response, but the universe doesn't care what you find comfortable. Well, let me give you a picture to hold in your mind, because this has to be concrete before it can be strained. That's always the rule with me. Image first, abstraction after. Close your eyes for a moment. Picture two rooms, room A and room B. Connected by a hallway, there's a single particle, a photon, and it enters room A first, where something happens to it. Let's say it gets its polarization rotated. A twist to the left, then it travels down the hallway into room B, where something else happens. A twist upward. Left twist, then upward twist. You get a specific result. Now run it the other way. The photon goes to room B first, gets the upward twist, and then travels to room A for the left twist. Different order. And because these two operations don't commute, which is a technical way of saying the order in which you do them matters, the way putting on your socks before your shoes is different from putting on your shoes before your socks, you get a different result. Fine. That's ordinary, classical, sensible physics. First this, then that. The order determines the outcome. Nothing controversial, nothing unsettling, nothing that would keep you up at night. Now here's what quantum mechanics actually allows, and what has been demonstrated in laboratories, starting in Vienna in 2015 and confirmed with increasing precision through to just last month. You can put the photon into a state where it goes to room A first and room B first. Simultaneously, the order of events are then B and B, then A. Exists in superposition. The photon doesn't have a definite history. It doesn't have a story you can tell in sequence, beginning, middle, end. It has both stories at once, and the two stories interfere with each other, producing results that neither story alone could produce. Results that no definite ordering of events could ever give you. This is called indefinite causal order, and it is not a thought experiment. It is not a speculation. It is not a philosophical position. It is a measured, verified, replicated fact about photons in laboratories that exist right now. And it means that the skeleton I mentioned, the one holding all of physics together, isn't there. But that's not the strange part. The strange part is how we got here, because the thread that leads to indefinite causal order starts, as a surprising number of the most important threads in physics do, with a phone call. And it's a phone call I love, because it's the kind of conversation that could only happen between two people who were both slightly crazy in exactly the right way. In the spring of 1940, a young graduate student at Princeton named Richard Feynman got a telephone call from his advisor, John Archibald Wheeler. Wheeler had an idea. One of those ideas that sounds completely insane until you realize it might not be. He said, essentially, Feynman, I know why all electrons have the same charge and the same mass. It's because they're all the same electron. Wheeler's picture was this. There's just one electron in the entire universe, zigzagging forward and backward through time, weaving a tangled world line that crosses the present moment billions upon billions of times. Every time it moves forward in time, it looks like an electron. Every time it moves backward in time, it looks like a positron. The electron's antimatter twin, identical in mass, but opposite in charge. One particle, one whirlwind. The entire material world is a single thread stitching through time. Now, Feynman didn't buy the full idea. There were problems with it. The most obvious being that we observe vastly more electrons than positrons in the universe, which is hard to explain if they're the same particle. But the seed of the idea that a positron could be treated mathematically as an electron traveling backward in time. That seed took root in Feynman's mind, and it grew into something enormous. It grew into the path integral formulation of quantum mechanics, which Feynman developed through the 1940s and presented in his doctoral thesis, and which earned him a share of the 1965 Nobel Prize in Physics, alongside Julian Schwinger and Shinichiro Tominaga, for the development of quantum electrodynamics. And the path integral is where cause and effect start to dissolve, where the skeleton begins to crack. Here's the idea, and I want you to feel how radical it is. In classical physics, Newton's physics, the physics you grew up with, a particle goes from point A to point B along a single path, the path. The one path that minimizes something called the action, which is a quantity related to the difference between kinetic and potential energy summed along the trajectory. One path, one history, one story. You can write it down, beginning, middle, end. Chord, mechanism, effect. It's clean, it's beautiful, it's wrong. Feynman said, no. In quantum mechanics, the particle takes every possible path from A to B, every single one. The straight path, the curved path, the path that loops around the moon and comes back. The path that zips out to the Andromeda galaxy and makes a U-turn and returns in time for dinner. The path that goes backward in time for a while and then forward again. Every conceivable trajectory, no matter how absurd, no matter how baroque, contributes to the probability of the particle arriving at B. Now hold your hand up in front of your face, point at the wall across the room. If I told you a photon goes from your fingertip to that wall, you'd picture a straight line, a beam of light, arrow straight. But in Feynman's picture, the photon takes every path, including paths that go through the floor, through the ceiling, out to Jupiter and back. All of them contribute. We'll try to picture that for a moment, not as an abstraction, but as a physical claim about what is actually happening in the room you're sitting in right now with every photon bouncing off every surface. That's the claim, and it's been verified to more decimal places than any other theory in the history of science. You're thinking, that can't be right. That's insane. If a particle took every path, we'd see that. We'd see particles looping around the moon. And you're not wrong to think that. But here's where it gets clever. And this is pure Feynman, this combination of mathematical power and physical intuition. Each path carries a phase. Think of it as a little arrow pointing in some direction. For the vast majority of the crazy paths, the arrows point in wildly different directions and cancel each other out. They interfere destructively. The arrows from the path that goes through Jupiter point one way. The arrows from the path that goes through Saturn point the opposite way. They kill each other. The only paths that survive the cancellation are the ones clustered near the classical path, the sensible, well-behaved trajectory that Newton would have predicted. So in everyday life, at human scales, you see particles doing sensible things. Light travels in straight lines. Baseballs follow parabolas, and everything looks orderly and causal and sequential. But at the quantum level, where the cancellation is imperfect, where individual paths don't perfectly cancel, that's where the strangeness leaks through. That's where particles tunnel through barriers they shouldn't be able to cross. That's where photons interfere with themselves. That's where the orderly story of cause and effect starts to fray at the edges. And here's the critical point for our story. In Feynman's formulation, there is no moment where the particle decides which path to take. There is no fork in the road. There is no causal chain that says first the particle considers its options, then it achieves. All paths happen. The particle's history is not a sequence of events. It's a superposition of every possible sequence, cause and effect. The idea that one thing leads to the next in an ordered chain, like links in a necklace, is not a feature of the fundamental description. It's something that emerges when you zoom out to the scale of baseballs and planets and human beings. At the bottom, there's no chain. There's a cloud of every possible history interfering with itself. Now, you might say, and smart, careful people do say this, fine, but that's just a mathematical trick. The path integral is a calculational tool. You add up all the paths because the math works, but you don't have to believe the particle literally takes every path. That's a story we tell, not a claim about reality. And that's a legitimate position. It really is. I take it seriously. But here's the thing. Every time we've devised an experiment to test whether the superposition of paths is real or merely mathematical, whether the particle actually takes multiple paths or whether it just acts as if it does, the answer comes back the same. It actually takes multiple paths. The interference is real, the superposition is physical, and if the superposition of paths is real, then the superposition of causal orders, which is just a specific kind of path superposition, is not such a big leap. It's the next step on a road we're already walking. And that next step was taken experimentally. Let me take you there. But first, 2007, a team led by Vincent Jacques in France, working closely with Alain Aspect, who would later share the 2022 Nobel Prize for his pioneering work on quantum entanglement, carried out a beautifully clean version of Wheeler's delayed choice experiment. This is crucial background, because the delayed choice experiment is where causality first visibly cracks, and if you don't see the crack here, you won't understand why it shatters later. The idea goes back to the late 1970s, when John Wheeler, yes, the same Wheeler from that 1940 phone call, still asking the most dangerous questions in physics nearly 4 decades later, proposed a thought experiment that should make anyone who cares about causality deeply uncomfortable. Here's the setup, and I want you to picture it physically. You have a single photon approaching a beam splitter, a half-silvered mirror that reflects half the light and transmits half. If you put detectors on both output paths, the photon shows up at one detector or the other, behaving like a particle traveling one definite path. But if instead you'll recombine the two paths at a second beam splitter before detecting, you get an interference pattern. The photon behaves like a wave that traveled both paths simultaneously. So far, so standard. This is just the double slit experiment wearing a different outfit. But Wheeler asked a diabolical question. What if you delay the choice of whether to insert the second beam splitter until after the photon has already passed the first one? After it's already decided, if that word means anything at all, whether to travel one path or both paths. Jacques and his team did exactly this in 2007. They used a fast electro-optic modulator, a device that can insert or remove the second beam splitter in about 40 nanoseconds, triggered after the photon had already entered the apparatus and passed the first beam splitter. The photon was already in the apparatus. It had already done whatever it was going to do with the first splitter. And then the experimenters decided what kind of measurement to make. The result was exactly what quantum mechanics predicted and what classical causality cannot accommodate. If the second beam splitter was in place when the photon arrived, the photon showed wave behavior, interference, meaning it had traveled both paths. If the second beam splitter was absent, the photon showed particle behavior, no interference, meaning it had traveled one path, but the choice of which measurement to perform was made after the photon was already inside the experiment. Think about what that means. Sit with it. The photon's behavior at the first beam splitter, whether it went both ways or picked one way, appears to be determined by a measurement configuration that didn't exist yet at the time the photon reached that first splitter. The future seems to reach back and shape the past. Now, I want to be careful here because this is where people get sloppy and start shouting about time travel and backwards causation. The delayed choice experiment does not let you send messages to the past. It does not violate causality in the operational sense. You cannot use it to build a time machine or warn yourself about next Tuesday. What it does show is that the classical picture of causality, where the past is fixed, the future is open, and events unfold in a single definite sequence, like dominoes falling, is not how quantum systems work. The photon doesn't have a definite history until the entire experiment, including the final measurement, is complete. Its past is not settled, and its story is not written until the last page, and the order in which you'd want to narrate that story. First this happened, then that happened. That order doesn't exist in any fundamental way. You're imposing it after the fact. Because the photon has no narrative. It has an amplitude. But that is not the strange part. That's the warm-up. That's the stretch before the race. Because in 2015, a team at the Vienna Center for Quantum Science and Technology, led by Lorenzo Procopio and colleagues, built the first quantum switch. And the quantum switch takes the delayed choice experiment and pushes it into territory that I think even Wheeler, who had the most adventurous mind of the 20th century, would have found dizzying. In a quantum switch, you have two operations, room A and room B from earlier, and a control qubit that determines the order. If the control qubit is in state 0, the photon passes through A first, then B. If it's in state 1, the photon passes through B first, then A. These are two different causal orders, two different stories, two different sequences of events. And here's the key. You put the control qubit into a superposition of 0 and 1. You put the order itself into superposition. A before B and B before A happen simultaneously. The photon has no definite causal history. There is no fact of the matter, not an unknown fact, not a hidden fact. There is no fact about which operation happened first. In 2017, Giulia Rubino and colleagues at the same Vienna lab verified this using what's called a causal witness, a mathematical test specifically designed to distinguish between definite and indefinite causal order, the way a Bell inequality distinguishes between local hidden variables and quantum entanglement. They ran the experiment, they computed the witness, and the result was unambiguous. The system had genuine indefinite causal order, not ambiguity about the order, not ignorance about the order. The order itself was undefined. And then, just last month, March 2026, Carla Richter and collaborators at the University of Vienna published results in PRX Quantum that pushed this even further. They violated a Bell-like inequality specifically designed for causal order, not by a little, by 18 standard deviations, 18 sigma. To put that in perspective, 5 sigma, a 1 in 3.5 million chance of being a fluke, is the gold standard for a discovery in physics. 18 sigma is so far beyond that threshold that the probability of it being a statistical accident is effectively 0. Now, loopholes remain. About 99% of the photons are lost during the experiment, and the apparatus hasn't been spread across large enough distances to rule out subliminal influences. But these are exactly the kinds of loopholes that existed in the early Bell entanglement experiments, and one by one, over decades, those loopholes were closed. The 2022 Nobel Prize went to Aspect, Clauser, and Zalinger precisely for that work. I expect the same trajectory here. The loopholes will close, the result will stand, and when it does, we will have experimental proof, not suggestion, not hint, proof that the order of events in the quantum world is not fixed. Now you're thinking, and this is the strongest objection, the one that deserves the most respect. You're thinking, maybe this is all just happening inside specially engineered laboratory setups. The quantum switch is a human-made device. Physicists built it to create indefinite causal order. Maybe this isn't something that exists in nature. Maybe it's an artifact of the apparatus, like a magic trick that only works when the magician controls the stage. And you're not wrong to think that. It's a serious objection. I'd be disappointed if you didn't think it, but here's where it breaks down. In 2019, Magdalena Ziek and colleagues at the University of Queensland proposed what's called the gravitational quantum switch, and the idea is devastating in its simplicity. Take Einstein's general relativity, which tells us that time runs slower in stronger gravitational field. A clock on the ground floor of a building ticks slightly slower than a clock on the roof, and this has been measured to extraordinary precision. Now take a massive object, a star, let's say, and put it in a quantum superposition of 2 different spatial positions. In one position, Alice is closer to the star than Bob, and so Alice's clock runs slower than Bob's. In the other position, Bob is closer, so Bob's clock runs slower than Alice's. The star is in superposition, and because the flow of time depends on the star's position, time itself, the rate at which clocks tick, the ordering of events, is in superposition. Any sequence of events that depends on the local flow of time, which is all sequences of events, is therefore in indefinite causal order, not because someone built a clever optical bench, because gravity and quantum mechanics together demand of it. We can't do this experiment yet. Putting a star in spatial superposition is beyond our technology by a wide margin, but the theoretical prediction is clear, and it follows from no assumptions beyond general relativity and standard quantum mechanics. If both theories are correct, and every experiment ever performed is consistent with both, then indefinite causal order isn't a laboratory curiosity. It's a feature of the universe wherever gravity and quantum mechanics coexist, which is everywhere, every room, every atom, every moment. So where does this leave cause and effect? See, I don't think cause and effect are wrong. That would be too simple, too clean. I think they're like temperature. Temperature is real. You can measure it. You can predict with it. You can build thermometers and engines and refrigerators based on it. But temperature is not a fundamental property of matter. No individual molecule has a temperature. Temperature is a statistical property. It emerges when you have a large collection of molecules bouncing around, and you average over their kinetic energies. One molecule has kinetic energy. 1 trillion molecules have a temperature. The property is real, but it's not at the bottom of the description. It's higher up, it's emergent, And I think causality is the same kind of thing. Cause and effect are real at the scale where you and I live. They're reliable, they're predictable. You can build bridges with them and launch rockets with them and plan your afternoon with them, but they are not fundamental features of reality at the deepest level we can probe. They emerge from something deeper, something that doesn't have a built-in causal structure, something where the order of events is not defined until a measurement completes the story. At the bottom, there is no first and second. There is no before and after. There is only the superposition of every possible ordering interfering with itself, and what we call cause and effect is the pattern that emerges when you zoom out far enough. This is, I think, the most revolutionary insight to come out of quantum mechanics, more revolutionary than the uncertainty principle, more revolutionary than entanglement, more revolutionary even than the measurement problem, because uncertainty tells you that certain properties of a particle can't be known simultaneously. That's a limit on knowledge. Entanglement tells you that distant particles can be correlated in ways that no classical mechanism can explain. That's strange, but at least events still happen in order. But indefinite causal order tells you that the very framework in which physics operates, the ordered sequence of events in time, the stage on which the play unfolds, is not a fixed stage. It's a quantum variable. It can be in superposition. It can be undefined, and the stage is part of the show. And this matters practically, not just philosophically. In 2019, an international team led by the Chinese physicist John Wei Pan demonstrated that a quantum switch can solve certain distributed computing problems exponentially faster than any process with a definite causal order. Exponentially faster, not a marginal improvement, an exponential one, which means that the breakdown of causality isn't a flaw in the universe's design. It might be a resource. The most powerful kind of computation might be computation where cause and effect don't apply, where the order of operations is itself a quantum variable to be optimized. There's a thread that runs from here directly into the deepest unsolved problem in physics, the problem of quantum gravity. In general relativity, the causal structure of space-time is the gravitational field. The order in which events can influence each other is determined by the curvature of space and time, and that curvature is determined by the distribution of matter and energy. The causal structure isn't separate from physics. It is physics. But if quantum mechanics applies to gravity, and it must at some scale, then that causal structure itself must be subject to superposition. The order of events must be indefinite, and that means that any theory of quantum gravity, any theory that unifies our two deepest descriptions of nature, must be a theory in which cause and effect are not assumed from the start. They must be derived. They must emerge from the theory the way temperature emerges from statistical mechanics. And this might explain why quantum gravity has been so brutally hard to construct. We've been trying to build it using tools that presuppose a definite causal order. But if causal order is the thing you're trying to explain, you can't assume it in your starting equation. That's like trying to derive the concept of heat while assuming that temperature already exists. Here's a thought experiment to make you feel the full weight of this. Imagine you are writing a history book about two events, event X and event Y. You want to determine which came first. You examine every piece of available evidence, you consult every possible record, and you discover that there is no fact about which came first. Not that the evidence is insufficient, not that the records were destroyed, there is no fact. X happened before Y and Y happened before X simultaneously. And the actual history of the world is a quantum superposition of both orderings. Your book cannot be written in sequence, not because you're a bad historian, but because history itself, at the quantum level, that doesn't always have a sequence. The events are real, the outcomes are real, but the order is not. Now, this part is my speculation, but I think there's something important here about consciousness, about the experience of being a thinking creature in this universe. We are beings who think in sequences. Every thought you've ever had has followed another thought. Every sentence you've ever spoken has unfolded one word after another. Consciousness itself, whatever it is, seems to require a definite ordering of events. They flow, a direction, a before and an after. And if the universe underneath has no inherent order, if causal sequence is emergent rather than fundamental, then the flow of time we experience is not a window onto the deepest layer of reality. It's a construction, something our minds build out of the quantum interference of unordered events. We don't perceive the universe as it is. We perceive the version of it that our causal, sequential, narrative-building brains can handle. There's more to pull on here. What happens when you try to build a theory of space-time itself as a quantum object where the geometry, the distances, and the causal connections between events are all in superposition simultaneously? And I think that's the frontier, the absolute edge of what physics can currently say. It deserves its own conversation because it changes everything about what we think space and time are. But here's what I still can't settle in my own mind, and I want to know if it bothers you too, if causality is emergent, if the order of events is not woven into the fabric of reality but arises from some deeper, unordered quantum structure. Then why does it emerge so perfectly at our scale? Why does cause and effect work so flawlessly for baseballs and bridges and heartbeats? Why is the classical world so exquisitely orderly if the quantum world beneath it has no order at all? Temperature emerges from molecular chaos. We understand that mechanism, but we do not yet understand the mechanism by which causal order emerges from causal indefiniteness. We don't know why the arrows all line up. We don't know why the story at our scale always seems to run forward. And until we understand that, the emergence of the sequential from the superposition of all possible sequences, I don't think we understand time. I don't think we understand cause. I don't think we understand the most basic feature of our experience of being alive. The play we call a reality might be all the possible plays at once. Every ordering, every sequence, every arrangement of before and after layered on top of each other in a shimmering quantum superposition. And what we experience, what we call the flow of time, what we call cause and effect, is nothing more and nothing less than the interference pattern they leave behind.